Okay. Hi, everyone. Welcome back to those who were here yesterday, and just a plain and simple welcome to those who are joining us today for the first time. I think how we'll begin today is by a very quick recap of what we spoke about yesterday. And we started the session yesterday by talking about what machine learning is in general and how machine learning sits under the umbrella of AI with multiple aspects of machine learning sitting within it, including deep learning, which is just a subset of ML and enables some very complex models to be built. Right? We also talked about how machine learning is an amalgamation of science, art, and math, where we try and arrive at inferences that are not heuristically very obvious or humanly computable unless you have something like a PhD. Uh, uh, and then the art of balancing the generalization of inferences against looking at each individual data point and what those data points have to offer, along with these two streams being enabled by mathematics that help us represent data in ways such that inferences can be drawn from them, and we use statistical and algorithmic methods to draw these inferences. Right. So how do we go about machine learning? The very basic steps are to gather data from various sources, clean up the data, merge the data, create homogeneity in the data, followed by selecting the right kind of machine learning model and building the model out, gaining insights from the model's results, and finally being able to visualize the model so that they are consumable. We talked about how steps 3, 4, and 5 uh, can always be iterated over and over again till we hit the required accuracies or the required business outcomes. Right, we spoke about this chart that gives us a very high level view of what the ecosystem of machine learning is and how we go about deciding what kind of a machine learning model do we have to build in a given circumstance, and the four different major areas of machine learning, which is classification, clustering, regression, and dimension reduction. We talked about how these four can be grouped into two key areas, which is supervised algorithms and unsupervised algorithms. The difference being that the availability of a labeled set to learn from leads us to supervised algorithms, and the unavailability of a tagged set to learn from brings us to the domain of unsupervised algorithms, where we are essentially trying to infer the inherent structure of the data. We talked about regression, which is a technique of fitting a mathematical function onto the data set that you have, such that the mathematical function describes that data set, in a generic format. And we talked about how these functions can be linear or polynomial, or could potentially any form of a non-linear relationship. We spoke about how to evaluate regressions, and the most common measure being an R-square minimization function that basically looks at each and every data point and calculates how far it is away from the generalized regression line that we've plotted. And essentially the optimization of regression is done by making sure that the total sum of errors is minimized for the entire system in general. Right, we talked about some of the issues that we can face while building such models. The most common being fitting problems, and models can be overfitted or underfitted, where underfitted models will basically be too general and will not be able to describe the shape of the data very well, whereas overfitted models will describe the data too well, such that the individual data points themselves become very important to the model instead of what the true representation of the distribution of data should be. And this leads to something called a high variance in the model, which means every time there's a new training set, the model will change drastically. Talking of variance and bias, we spoke about how bias is essentially overtly simplifying a particular model such that the amount of predictive power it has is very low. And we saw that in this particular use case on the left hand side, where we are plotting a first degree linear model, uh, there's essentially very high bias in the model. And you can see that the distances that each of the point has from the model function are very high. On the right hand side is a model which has very high variance. You can see that the distances are very, very low, which means that the model tries to pass through as many data points as possible. And what this causes is a variance error where every time there is a change in the training data set, the model definition itself changes by a large amount. We also talked about when building models, how do we do a trade-off between bias and variance? And in general, the trends are that linear machine learning models often have uh, very high bias but low variance. But nonlinear machine learning models have a very low bias but a high variance. And we have to make sure that we get the right fit uh, for each of the for each model that we build. Just that it's the just right parameter optimization that will lead us to a model that is neither very high in bias nor very high in variance, so that it can not only represent data in general but also is robust towards more and more data being uh, you know more and more data being fed into the model, and the model does not change a lot over time. Then we talked about classification, and how classification is a technique of fitting mathematical functions as boundaries between groups of data, such that all new observations that come in that need to be classified can be located on either side of the boundary, and can therefore be classified into a set. Uh, we talked about some of the classic techniques. We talked about the support vector machines. We talked about logistic regression. We talked a bit about random forest as well. And essentially, what all of these do is that they create these boundaries. Now, support vector machine creates a wide boundary that has margins on both ends and allows us to really create these robust models. We'll also talk about logistic regression today as a live example, where we'll see how the model, even though it's a regression, essentially does the job of classification. We also understood that classification is also bound to the same underfitting and overfitting issues, and therefore bias and variance issues. And it is therefore important to make sure that parameter tuning is done right, so that we are not underfitting or overfitting our models, leading to higher biases or higher variances. We looked at how to evaluate our models, where we talked about a confusion matrix. We talked about precision and recall values. We talked about an F score that is available from the confusion matrix. In this given example, the precision of the model is 99.6%, but the recall of the model is 85.7%. And overall, the model performance, if we have to do one metric for it, we do an F score that is represented as 1 comma 1 plus 2 comma 2 over the total, which is 88% in this case. If you remember, we also talked about the importance of precision and recall in terms of cancer predictions, where it is important to tune the model such that it is a very high recall model. But then we also have to look at the business, where if that model is just saying everybody has cancer, then it does not work very well, right? Then we saw what lift or gain charts are. We saw how to evaluate area under the curve charts, where we are plotting the true positive rate over the false positive rate, which is basically a measure of precision, if you notice. And you'll see that in this one, in this chart area, which is 1 x 1, so 1 unit of, 1 unit of area, if the precision is 99.6%, you will notice that the area under the curve is 99.6% of the area that the chart represents. So this is another way of visually understanding what the precision is, and how to essentially, check if we are at a good precision rate or not. Now, one thing that we didn't talk about yesterday, and I apologize for that, is how do we decide when to actually stop tuning our model so as to increase precision. Now, if you look at the left-hand chart of the second row, you'll see that this is an ROC chart. You will see that there are multiple steps and elbows over there, but essentially what is happening is that there is a huge raise in precision as the false positive rate increases towards the beginning, but then it tapers off towards the end, right? So if we see from this particular chart, there is no gain in precision once the false positive rate hits about 0.6, and then further improving the model is not going to help us. Also, if we are okay with a lower precision, and because every time we try to increase precision, recall will take a hit, and recall will go down, which means that this really helps us in understanding at what point we should stop where the chart is essentially stagnating on the precision scale. On the right hand side is a much more smoothened and general way this thing works, where precision rises very sharply in the beginning but then tapers off, and then it is up to us to find the elbows here to identify what are the best areas to create our cutoffs and optimize our models. We talked about reducing bias and variance in our models by cross-validation, where essentially 1,000 observation data set will be divided into 10 different subsets, and we'll do 10 rounds of training, where we take 9 subsets for training and 1 for validation, and then keep changing the validation set so that every data set or every subset has been used in training 9 times and validation 1 time. We talked about clustering, which is the automatic grouping of observations based on their inherent properties, and we saw how it brings out the differences in each other, in an automatic manner. We talked about how to get differences from each individual data set, and we talked about the distance metrics that can be used, the popular ones being Euclidean and Manhattan. And on the right hand side, we talked about how do we represent the distance matrix. Now, all of this is a lot of numeric data, and of course numeric data is very, very important in the enterprise scale. So there's one more area of data science and machine learning that is equally as important and deals with a completely different data set. And today we'd like to talk about that. And that is analyzing text data. Right? So what is text data? Text data can come in so many different forms and has so many different use cases across enterprises. Text data could come in as, for a company, it could come in as social media reviews. For a product, it could come from forums. For example, you've got a product that aggregates news. So all of the news in the world, all the articles, etc., become your data set. You can have you can have various different topic aggregation from the internet happening internally. It could be let's say, all the transcripts from customer service phone calls, right, to identify what are the key issues that customers of a company have, to identify if a particular issue or issue topic is spiking or not, to identify what are the pain points that a company can solve for its customers. So all of these use cases have a lot of text data that needs to be analyzed. So how do we analyze text data, and what all can we do with it? Right? There are lots of popular solutions that have got widespread acceptance, including topic modeling, sentiment analysis, topic evolution, creating these word clouds, and creating these phonetic and contextual similarity and matching solutions. So we'll go one by one and try to figure out what are the key aspects of each of them. So topic modeling basically is the automated identification of inherent topics in a text data set. Now, how does it do it? How does it identify what topics are? It assumes that uh, each text document, and one document is basically one piece of text in the world of text analysis. So each piece of text or each document derives information from multiple generic topics in order to create the content. And let's say you've got 100 documents, they could be talking about 10 or 15 different things in general, and each of those documents talk about 3 to 4 or 5 different kinds of topics. So while the numbers can change, the theory behind topic modeling is this. What topic modeling does is it tries to gather the inherent relationship between the words, and uh, transform that into a manner that tells us what are the what are those words that group together very well, and therefore form the basis of a topic. And from that we can also understand each document picks out from which of these bags of words, where each bag of word is nothing but a topic, and within that topic each word that is there comes with a probability. The visualization that you see on the left hand side, top row left hand side, is a representation of the same, where you'll see that this is, if I'm not mistaken, data taken from Twitter, where each tweet is a document. And this was this was an application. In fact, I had built this application, and this was essentially looking at. Hello. Yeah. Okay. And this was essentially scraping Twitter for all tweets related to big data. So of course, and this was about 4 or 5 years back in the day. So there was a lot of Hadoop and a lot of Hadoop and Apache and everything sort of came a lot. So you would notice that each of these topics that are colored individually had Hadoop as a keyword. But then when you start looking at others, the one in blue talks a lot about careers and jobs and software engineering and development and hiring, etc. So this is a bunch of tweets about people wanting to hire or trying to get hired as Hadoop or big data developers. The light green, you'll see that there's a lot of talk about data and table and Intel and research and Xeon. So this article refers to potentially hardware that enables big data. And if you look at Intel and Xeon, and we remember a few years back, there was a big push towards commodity hardware on Xeon processors for big data processing. I'm sure that this is a topic that comes from there. The dark green one is, let's say, Hadoop, Asia, mobile, cloud, world tour, stories, boom, skills, etc., which tells me that this is fairly close to something that talks about Hadoop and big data in the media, and potentially world tour could potentially be around conferences, etc., that are happening. So this gives us an understanding of what uh, these set of documents might be referring to. Then the next big use case is sentiment analysis, where of course in a classic uh, use case like customer uh, like customer phone calls or customer feedback, etc., what is their sentiment, how do we calculate their NPR from all of this data. The third one that you see is, uh, let's say monitoring tasks. If we have a social media feed and we want to monitor it and see what kind of topics and what kind of sentiments are there, this is one view that essentially tells you at a point in time what are the topics that are there in your social feed and how they evolve over time. Then of course, just the simple representation of words as a word cloud, where the size is the frequency of the word, is a very popular way of just getting a very basic idea of what the what the entire data set talks about. And finally, one of the key and most important areas of text processing or text analysis, but not so famous one, is matching, where essentially being able to match two different text data sets based on certain properties. And it could be things like phonetic similarities, it could be a dirty data set versus a clean data set, and trying to match them by looking at spelling differences, by looking at out of order components, missing components, by translations, essentially multiple languages, by similarities or truncations that might be there. So this in the enterprise becomes a very, very important use case. Right, so let's talk about some of the basic structures that go into text analysis, right? And the first basic structure is a document term matrix. What is a document term matrix? It's essentially a representation of this unstructured text that we have into a structured lexical form, where we can have rows as documents and columns as terms, or the other way around, which is a term document matrix, rows as terms and columns as documents. And we break down each document into its terms, and we say, for example, in document one, complexity comes twice, algorithm comes thrice, entropy comes once. Similarly, in document 3, complexity comes thrice. In document 4, complexity comes twice, so on and so forth. Now, how do we decide which terms are important and which ones are not? And therefore, how do we normalize this entire thing? Because the reason we have to normalize is that the length of documents might be different, the context of documents might be different, and the way the documents are written might be different. So we look at two different things. It's a combination measure of term frequency and inverse document frequency. The term frequency that you see is basically given the term complexity, algorithm, entropy, etc. in a document. For D1, the term frequency of document would be 2 divided by, let's say, 6, so 1 by 3. Right? So if there are a total of 6 terms in document 1, the term frequency of complexity would be 2 by 6 or 1 by 3 in this case. Algorithm would be 3 by 6 or 0.5, and entropy would be 1 by 6 for document 1. Similarly, for document 2, which has 3 terms, we'll have 0.66 and 0.33, so on and so forth. Then we are going to look at another measure called inverse document frequency. What that tells us is that for a given term across all documents, how many documents was it a part of, right? So we'll basically see complexity. Complexity is a part of 4 out of the 5 terms. So 4 by 5, and then we inverse it, which makes it 5 by 4, right? And take a log of it. And when we take a log of it, what this tells us, what this does, is that it gives us a measure of the importance of this particular term in this data set, right? Now, a term like the will be very common across a lot of documents, and therefore will have a very high term frequency across a lot of these documents. But the power of the term the, in order to differentiate documents from each other, is very low, because it is a high frequency term across all different documents, right? So its inverse document frequency is going to be very low. The example on the right hand side that you see, where the is available in both uh, document A and document B, uh, essentially has an inverse document frequency of 0, because it is there in both the documents in this data set, right? So similarly, what we get is a TF-IDF score for each term in each document. And one after multiplying, we see that car and truck, as well as road and highway, are the 4 words that really differentiate these two documents. What are these two documents? They are basically two. The car is driven on the road, the truck is driven on the highway. So the differences are really car versus truck and road versus highway. And that comes out very well when we do a TF-IDF for this data set. I'll stop here and take any questions if anybody has any about text analysis in general, or document term matrices and representing documents as document term matrices. Okay, all right. So moving on, how do we use this document term matrix? Now, this document term matrix is the base structure that feeds into the topic modeling algorithms, where there will be 2 topics essentially derived from here. One of the topics will have car and road, the other topic will have truck and highway. And that is how, you know, uh, topic modeling is done. Now, when we have a much larger data set, of course, the mathematics starts kicking in and tries to derive these topics out of a much larger data set, where the numbers are not that clear to the human eye. But this becomes the input structure that a topic modeling algorithm like latent Dirichlet allocation or the Chinese restaurant process, etc., will take. This can also become a very easy way to do a very simple sentiment analysis, where we can have words categorized as 3 different bins. We've got positive words, negative words, and words that don't have any sentiment. And if you can multiply the TF-IDF score for each individual word in a document into their probability of positive or negative, we can get a very simple sentiment analysis from here as well. Of course, today there are a lot more complex models, and there are deep learning models that work on hierarchy and context, and essentially have a lot better accuracy. Uh, but they still, this is one of the core structures that will help us in getting to those complex structures as well. Right now, let me move to the another big way of representing text using mathematics, which is word vectors. Now, word vectors is the representation of a vocabulary in an n-dimensional Euclidean space, so that the inherent relationships between them are captured by their distance and directionalities. To simplify this, imagine that you have all of us have gone to school and plotted these graphs. Right now, if I were to plot different points on a graph and make sure that their relationships are essentially maintained, this is what word vectors does on a much larger scale. And what do we mean by an n-dimensional Euclidean space? A graph on which we plotted was a 2-dimensional Euclidean space, or a space where you can plot stuff. A 3D chart like we have on the screen right now is a 3-dimensional Euclidean space. Similarly, there can be n number of dimensions in mathematics on which that you can use to plot and essentially get the location of each individual word. Now, what word vector does is that it takes in such an n-dimensional space, it will plot each particular word and represent that word as a set of locations on axis. For example, in this case, king could be denoted as 1 comma 1 comma 2, and man could be denoted as 1 comma 1 comma 3. Queen could be denoted as 1 comma 2 comma 1, whereas woman would be 1 comma 2 comma 2, right? But what is important to understand is king is denoted in terms of numbers or a set of numbers. Man is denoted as a set of numbers. Queen is denoted as a set of numbers, and as is woman. Now, what we've done is very similar to what we did in the documenter matrix. We've taken this unstructured data, which is text, words basically, and we've given it a structured lexical form, right? Now, the specialty of word vectors and the creating word vectors comes from a deep learning model, or there are now multiple deep learning models that help us create these binary representations of words. But to simplify it, what this will do is that if you take the vector for king, subtract man, add queen, add woman, you'll get the vector for queen. If you take the vector for swimming, remove walking, add walked, you'll get swam. And how is this possible? This is basically because these are just numbers in a graph. You can subtract these vectors from each other. And now what is a vector? It's nothing but when we say 1 comma 1 as a representation on a graph, it is basically the vector, or the line that goes from 0 comma 0 to the location, which is 1 comma 1. And this vector has a size and a direction, right? The size is basically the distance, and the direction is basically the angle from 0 degrees that it is at. Similarly, each vector, has a size and a distance, and it is possible to mathematically subtract one vector from another in order to get the resultant. Now, think of a triangle. If you subtract in a right angle triangle, if you subtract from the hypotenuse the base, you will get the vertical. Similarly, if you subtract from the hypotenuse the vertical, you will get the base. If you add the base and the vertical, you will get the hypotenuse. Another example of what word vectors can do is that, in a represented word space, if you take, let's say, Turkey and subtract Russia, but add Ankara, you will get Moscow. And this becomes a very easy way. Think of a statement like, hey, what is the capital of a given country, right? So if we have, for example, we say, what is the capital of Spain? The easy way to derive it is that Spain plus capital should give us Madrid, right? And this becomes very, very important in advanced natural language processing and advanced natural language AI. That really is, what's happening around the world today with a lot of with your Alexas and your Cortanas and Siri and Google Assistant, etc. And this really is what forms the core of each of these natural language understanding software. Can I take any questions at this point in time? Okay. Now, we have a bit of time today, luckily, so we'll jump right into code. Unfortunately, I can't, I don't have enough time for everybody to run the code, but what we'll do is we will send across, or at least, share a link to these code snippets that we have so that all of you can try it out and essentially learn from it yourself. So, linear regression. We talked about linear regression, and how we do linear regression is essentially we import a few libraries. Now, pandas is one library in Python that lets us do a lot of numeric computations as data frames. A data frame is nothing but a representation of a table in Python. So we read the training data set and the test data set. If you remembered when talking about validation, we divide our data set into training and test. This can sometimes be done offline and sometimes has to be done inline. What we've chosen to do right now is essentially pick up the training and the test data set separately, right? Looking at the data, we do a data.head that gives us the first 5 or 6 rows of the data so that we can get an idea of what it looks like, right? We printing the shape of a data tells what the dimensions of the data is. So our training data is 341 rows with 36 columns. Again, testing data is 341 rows with 36 columns. Now, in order to predict, what we've got to do is we've got to separate the independent variables and the target variables. So we are basically removing item outlet sales from our training data set. Let me show you what item outlet sales is. So we want to predict sales using our regression model. So item outlet sales is what we remove from this and say that this is going to be our target data, right? We do the same to our test data set. Now, creating the model is as simple as writing model.fit train data set and test data set, where the model is a linear regression model, right? It's actually quite simple while doing this, but of course there are a lot more when we do a model.fit, there are a lot more different kinds of variables that need to go in, and to understand the degrees and the how overfitting, underfitting, etc. happens. There are more workbooks that are there that will be shared where all of these parameters are explained. If you look at this, number of jobs equal to 1, normalize equal to false. So it has taken default values for all the other parameters that are there, right? Now we've got the model coefficients and the model intercept. Now, what is the coefficients and the intercept? If you look at, this is a line, right? So this will have an intercept on the y-axis. That becomes the model intercept. And the coefficient is, for each of these x values for which we trained the data, what is the, for each of the x values, what is the y value on the line, right? So these are the coefficients of the model, right? We basically subtract each individual y value from our trained data set with these in order to identify what the errors are, right? And that is what we are doing in this place, which is the root mean squared error, right? We are getting the mean squared error from all of these, and we see that the error is 939, right? On the test data set, we do the same thing and we get the same result, because essentially in this case, the data set is the same. But when you will be doing it, you will most likely have a different train and test data set. So your errors on your data set will be low. Now, how do we know that this is a good model or not such a good model? Of course, we haven't done any sort of optimization on the model. Let's go back up. And we see that sales are about 1700, 3300, 3400, 1600, 1300. So an error of 900 on 1300 or 1600 or 1700 is very bad, which means that this is a very simple model. And if you remember, what we talked about in bias versus variance, this is a degree 1 model, which is linear and has a very high bias, and therefore is able to predict horribly on this data set, right? So we'll have to optimize this model in order to make sure that this is not a degree 1 model, the bias reduces, and we are able to predict better. Now, logistic regression. If you look at this chart, logistic regression is plotting an S curve between two different classes of data, and you will see that this is a binary classifier, which means it classifies data into 0 or 1. And what this will do is this is going to fit this S curve, and it'll have two cutoffs, one on the left hand side, one on the right hand side, and wherever the middle of these two cutoffs lie, it will basically divide a line and say that one side is 0 and the other side is 1, right? So how do we do a logistic regression? Similarly, in a very similar manner, we basically train and pick up our train and test data set. The model becomes logistic regression and we fit it, right? In linear regression, based on the parameters, we were fitting a line, or we were fitting a curve, or we were fitting a hodgepodge, basically, depending on whatever the function is. In logistic regression, the function is defined, but how tight, whether this is going to be, let me see if I can annotate this, right? Whether this is going to be annotate, draw. Okay. Yeah, okay, I can annotate. Excellent. So whether this is going to be something like this, or it will be a model that will be like this, both of these are valid as curves. By the way, can all of you guys see the annotations? Well, I'll assume yes, right? So depending on the parameters, it will fit a tight or a loose S curve, and that is what allows us to do these annotations. Sorry, do these different forms of models and different categorizations in this model. Okay. Okay, so moving on, we again calculate the accuracy of this using uh, the accuracy score test, which is the F score, and we'll see that the accuracy score on the trained data set is 572, which tells us that there is a root error of out of all the different points that we had. Wait, let me find out what the number of points were. Yeah, 712, 25 and 179, 25. So the accuracy tells us that out of 712 rows and 25 columns, I was able to get 529 correct, which is a fairly decent model. Here is 572. So this is a fairly decent model that we've built. The next is a decision tree, right? What we basically do is in a decision tree, if when we read the data, each of the individual variables of data, right? We are reading the same data set as this one, right? We see age, fair, and we see all of these. We see whether it's a male or a female sex. We see some class. We see some, multiple different columns. Now, what we want to do with a decision tree is that we want to pick up at every different uh, level one particular variable. Let's say play. There are 13 observations that say play and 9 that say don't play. So we divide this into multiple ones, and then we look at what the overcast, what the outlook is, what is the weather. Weather has 3 different ways of looking at it. So we've got sunny weather, overcast weather, and rain weather. So for sunny weather, we've got 6 play and 6 don't play. For overcast, we've got 4 play and 1 don't play. We've got for rain, 3 play and 2 don't play. So for overcast, we can make a decision that if it's overcast, then play, because for Sunny, there's a 50-50 chance of playing or not playing. So we look at another variable. In this case, we're looking at humidity. So if it's very humid, 5 of them say play, 3 of them say don't play. If it's less humid, 5 of them say play, 3 of them say don't play. And if it's very humid, 3 of them say don't play, 1 of them says play. So if the humidity is very high, then the decision to play or not to play is essentially don't play. Right. Similarly, the entire decision tree gets created based on these cuts of data at every level. Right. We've got some sample code that will help you create your own decision classifier. So please go ahead and do that. Now, finally, we'll look at a support vector machine model. And what a support vector machine does is that, if you've got data that needs to be clustered in two different, so that needs to be categorized into two different groups, it will create a boundary between these two groups, and then it will create margins that define, between the boundary and these two groups, what is the no man's land. Now, every time there's a new data set or an observation comes in, depending on where it is plotted, if it is plotted uh, one side of the boundary versus the other, it will be able to tell you, whether this is category A in this case or category B in this case. Again, please try out the code. This is again Python, so it's very simple. Your model you just have to define. It's a support vector model, which is defined by SVC, support vector classifier that is, and you just have to do a model.fit, right? Prediction is again very easy. We say in order to predict, all we have to do is model.predict on the training data set, and we get all these targets, essentially all the predictions. Calculation of accuracy score is again very simple. This will give you a simple percentage accuracy score. So we were 65% accurate on the training data set, but on the test data set, we were 72% accurate. Often happens that our training data set accuracy is higher, our test data set accuracy is lower, but in this case, our test data set accuracy is higher. That tells us that we've actually built a fairly decent model. Finally, let us very quickly look at k-means, which is a method of clustering, right? We've spoken about how k-means creates their clusters. So, I'll let you guys go through the details again here later in order to, for you to pick it up again. But when we essentially get training data set, and we have absolutely no target variable defined, we don't know what to learn from it. What we'll do is we'll try to group all of these together. Now, one of the key things is how to decide what is the right number of clusters that k-means will have to divide the data set into. And what we do for that is we run k-means with multiple numbers of clusters. So essentially, we are running multiple models. And then there is a metric called cluster withenness or intercluster distances that tells us on an average what is the distance between all of these different clusters. And we'll see that there is some sort of a, somewhere in the chart, there will be an elbow. And that elbow is normally where we say that the value of clustering into more clusters is now no longer there. So again, there's some sample code for you to try out and do your first clustering. In this case, we've done clustering into 3 clusters. But what I'll really want to show you is a case study on how do we mix multiple models together in order to come to a solution, and also show you, give you a walkthrough of how do we sort of do it for text data as well. So what we are going to try and do is we are going to group together news articles into topics, or not just topics, but into sets that can be defined as, uh, that are defined as news with similar content, or news that pertain to similar things, we want to group together. And uh, while topic modeling is a good way of solving it, what I wanted to do was show you this thing using word vectors. Now, we are not going to build a word vector model ourselves. In this case, we are going to use one that Stanford has already built and open sourced. So what we do is we essentially download a bunch of packages that are required to build this out, build the solution out. We've got, requests, NumPy, pandas. Jensen is what essentially allows us to read the word to vector model. Scikit-learn is the machine learning, the generic machine learning package from Python. Math SciPy is your essentially your scientific computations and vector computations package in Panda. NLTK is your natural language processing package in Python. So what we do is we essentially first hit an API to get all of these articles, and we are using newsapi.org for it, right? This API returns a JSON. So what we'll do is we'll get all of these articles from these JSONs, and we are going to uh, essentially put them into a particular data vector. A data vector is nothing but a list of all the news articles that we have, and how this looks like. Oops. Okay. I think these are all the headers or topics of of all the news articles. So this is how all the topics look like, right? For this use case, we are just going to stick to trying to group together these news headlines. Right now, what we do is we essentially pick up this pre-built model that we downloaded from Stanford, and assign it to this variable called model1, right? What we'll do is we will get the word vector for each individual word, right? If you remember, when we spoke about word vectors, each individual word is represented in the n-dimensional space. In this case, I believe it's a 300-dimensional space, and each word essentially becomes a vector in this case. Now, because a vector on a vector we can do mathematical calculations. What we can do is, for example, see the world's coolest ski lifts, right? It has 1, 2, 3, 4, 5, and 6 different words. So we'll get 6 different vectors for this, but we can take an average of the values in each dimension to get the average vector for this particular sentence or this particular headline. And this is what gives the power to using word vectors, because we can scale it out to sentences, we can scale it out to phrases, we can scale it out to entire documents if needed, right? So see the world's coolest ski lifts, we'll get 6 vectors, we'll take averages across each dimension. So my 6 cross 300 matrix becomes 1 cross 300, and we've got one final vector of the length 300 for this particular document, right? And this is how this is going to look for each. Okay, I haven't actually shown it to you, but for each individual header or headline, we'll have one vector, right? Next, what we'll do is because now we've got these 300 dimensions. Imagine that these are these 300 columns. We'll just do a simple k-means on top of it, right? Because we want to cluster these, and k-means is very happy to deal with numeric data, right? So we run of course, we have to do this step called a scalar transform that takes the data set and transform it into a scaled data set that k-means can accept. And finally, we say that we want to group it into 5 different clusters. And again, 5 different clusters is not scientific at this point in time, but it's just an example, right? So once we have the clusters, you'll see that each of the headlines is clustered into a particular cluster. We see CES 2020 in photos, living the material world is in cluster 4. You see, here's what the world will look like in 2030, which is also future looking, which is in cluster 4 again. You'll see cluster 3 that talks about Ubiquity 6, that talks about Van Dyke for Liverpool, that talks about Stephen Colbert, Monster Hunter, uh, Niantic, etc., which gives me the feeling that it's a very lifestyle-oriented group, but essentially all of these get clustered into one. Now, if you want to look at one particular cluster and everything that's there in it, we see that the world of Watchmen, watch an annual solar eclipse, wild things in extreme weather, how to get a divorce, it seems, how to spot fake news, how to watch. So essentially, things that you can do or things that uh, you know, uh, headlines that are driving you towards doing something are essentially clustered in the first cluster. So this was just a quick walkthrough of the power of word vectors and how we can essentially transform our data set, a text data set, into a numeric data set and analyze it and derive such inferences. There is another case study that essentially groups event names into, so we've got the Monster Jams grouped into one, we've got the Eagles games grouped into one, we've got Clippers versus Lakers grouped into one, we've got LA Kings versus the Ducks grouped into one, and we've got all the F1s grouped into one, which follows a very similar process. The only difference is in the input data, right? So this brings me to the end of, I think we're also out of time. This brings me to the end of today's discussion, albeit I'd hope that, there would be more of you joining in the discussion, but that's fine. What we'll be doing is, I think I'll be sending across all of this material to Neelam, and, Neelam, if we can find a good way of either putting it into a G drive or distributing it somehow, I think all of you will have access to this material as well as this, reading material in the presentation. So please go ahead and look at it again, refer to it again, and the idea of these sessions really was to give you an overview of what are the different areas that that Accion in specific and the data science community in general is looking at in terms of extending AI capabilities, and how each of you in your day-to-day work, everybody deals with data, right from ETL guys to developers to, of course, data scientists as well. But the idea is that every time that we're trying to solve a problem, the fact is that every problem has data associated with it. And how can we, in customer situations, identify that a problem or there is a problem which is a data problem and can be solved, and essentially this helps Accion in general and all of you as individuals to have a lot more insight into the problem want to continue down the road of becoming machine learning developers are most welcome to. And this was these sessions hopefully will tell you what kind of work happens in this space, and will get you interested. So thank you, and over to you, Neelam.